Hey, good morning, everyone. It's 11 a.m., so we'll go ahead and get started. Max, are you ready to go?
I am ready to go.
All right. Well, we'll go ahead then. But again, good morning, everyone. We appreciate you joining us for this edition of the TPM Technical Webinar. My name is Aaron Smith. Here at TPM, I'm in the 3D printing division as an account manager, and I serve the South Carolina, Georgia, Alabama, and Florida locations. So if you have any questions at the end of this webinar, you can direct those directly to Max and myself, and we'll get those answered. So with that, I'd like to introduce Maxwell Ames, who is the Technical Solutions Consultant. Today, he'll be presenting the Design for Additive Manufacturing webinar. So in this webinar, we'll cover the understanding of the core concepts for designing for additive, how to apply the core concepts of design for additive to a real-world problem. We'll take the results of the application and print a component that is more cost-efficient and functional. So with that, I'll go ahead and turn this over to Max. Hope everyone enjoys.
Awesome. Thanks, Aaron. All right, everybody, let's get started. So, understanding design for additive manufacturing is all about mindset and tool set. And by mindset, I mean thinking about ways we can accomplish things by thinking outside of the box. And by understanding why we can design in new ways that were off limits in the past. So, let's start by using a sheet metal example to think about how we might traditionally go about designing a component and then relate it back to additive manufacturing. So when we talk about learning new processes, it's always a good idea to relate the new process back to an old process that is fairly well known. So for example, when designing for sheet metal, how do we go from the left-hand side of the screen, which is a CAD model in SOLIDWORKS, to the right-hand side of the screen, which is an actual physical completed sheet metal part? This process on the screen is a very simplified example of how to do so. There are three main stages that typically happen in any design process, and sheet metal design is no different. These processes are, number one, defining the problem statement. What problem are we solving? Are we making a simple bracket that's mostly cosmetic? Or are we designing a bracket that holds up an engine block and needs to have dampening properties? Number two, determining what tools you have available to you. Do you only have a hammer and a bench vise available to you? Or do you have a CNC press brake? Do you make your designs on the back of a napkin? Or do you use SOLIDWORKS to design your sheet metal parts? And then finally, number three, what solutions can you gather from the problem at hand and the tools available to you? Can I make a sheet metal bracket from my napkin drawing and my hammer and vise block? Maybe I can. Can I use SOLIDWORKS to design an intricate sheet metal part and then use my CNC press brake to make my part? Without a doubt, I can. And once you come to a possible solution, you try it out. But this isn't always as easy as it will be. What if the part breaks in operation and you need to redesign the part for more loading? What if the part you need to make won't fit in your press brake? When thinking about how a design process actually works, we always need to think about how we can make changes to it too. So that's why we have the arrows pointing back to the first two steps. This process is always moving and evolving depending on what's happening. So what about design for additive manufacturing? It's almost the same. This process still maintains the three core stages, and all that changes are the additional problems we can address and the tools available to us to use. So number one, defining the problem statement. What problem are we solving? With metal and plastic 3D printing, we can address even more problems than we could before, but we still need to make sure that additive manufacturing is the best fit when compared to traditional methods. Typically, this comes down to cost. Then number two, we need to determine what tools we have available to us. This section is where design for additive manufacturing differs the most from traditional manufacturing processes. We have essentially all the same traditional modeling methods available to us, and then some very new modern practices that have come out more recently. And then finally, number 3, what solutions can you gather from the problem at hand and the tools available? If your main objective is to lightweight a component and have it produced very quickly, do you have the tools available to do so? Does your design software allow you to easily model complex geometry in order to lighten your design and maintain your factor of safety? This section is typically where most of the confusion comes from in the design for additive space, simply because of education. New 3D printing processes are coming out every day, as well as new modeling software, and it's our responsibility as designers to understand the capabilities of each process. They are rarely the same, and they always have huge benefits. So let's take a look at a real-world example where we used our design for additive process to take full advantage of 3D printing technology. What we're looking at here is a test fire of a robotic ball launcher. This robot was designed by a FIRST robotics team up in Charlotte, North Carolina, and was designed completely by the students. The robotics team's goal is to launch the yellow balls through the air and hit the circle up on the wall. Once the robot is out of balls to launch, it moves backwards, simulating a match, and then the students load more balls in. The robot then moves back to the firing line and shoots again. This may seem fairly simple, but the design behind the scene is quite complicated. One of the interesting things to note here is that every time the robot goes back and forth, it doesn't always go to the same spot, but it always hits the exact same spot up on the wall. The firing mechanism operates very similarly that, excuse me, sorry, I think I skipped a slide here. There we go. This robot is unique because it uses an onboard vision system, which is circled in red to track the target, and also to auto-range the firing mechanism to hit the target. As the students drive the robot around the playing field picking up balls, all they have to do is to hit a button and the robot will auto-lock onto the target and get a correct range. Then when the students hit the fire button, the robot launches the balls and scores points. The CAD model for this firing mechanism is shown on the far right of the slide. It was designed in SOLIDWORKS solely by the students. Firing mechanism operates very similarly to that of a baseball pitching machine. The white wheel on the left-hand side of the assembly picks up a ball and spins it through the feeder and launches it up through the top of the assembly, which is upwards in the picture. This component was originally designed to be 3D printed using HP multi-jet fusion technology, and it has worked very well. But there is definitely room for improvement. The component is quite heavy and needs to have a significant amount of its mass removed while still being able to hold up against the launch pressure of the ball. So how do we use design for additive manufacturing to solve this problem? Let's go back to our 3-stage process and see if we can make sense of what to do. So let's talk through the problem statement, the tools available, and the possible solutions for this application. So starting with the problem statement, we've determined that the loading conditions are approximately 20 pounds of force on the front face of the component. Our end point for the needed factor of safety is about 1.5. We've determined this simply because the loading will never exceed 1.5 of the yield strength. Our material choice for this project is still PA12, which is one of the primary materials for the multi-jet fusion printing technology by HP. We need a lighter design. It's one of the main goals of this project. We need to reduce the mass as much as possible while still maintaining that factor of safety of 1.5. And as a side note, it would be nice if this component, this new component, was cheaper. It has to be cheaper than it was before. This is sort of going to be a side effect of reducing the mass, but it's still something we need to pay attention to. One of the very key components of this new design is that it must use the same mounting hardware as before. We don't want to redesign the components that made up to this component. So we're going to use the same fasteners and the same dowels to line it up. And then last but not least, we're in a time crunch. As always, this project is due yesterday, so we have to do it quickly. We have to design quickly, figure out how we're going to produce it, and then actually produce it within a very small window of time. So let's switch over to our tools that are available to us. The tools that I personally have to do this project are SOLIDWORKS, SOLIDWORKS Simulation, and a new software called nTopology. What manufacturing hardware do I have? Well, our primary printer that's driven by our material choice is going to be the HP multi-jet fusion printers. Now, if I needed to print on the multi-jet fusion printer, but it was busy, I could outsource this job to some other service bureau and they would make me pay a premium, but it's still an option. And then finally, on the third bit there, what are the possible solutions? So for this solution, I'm going to show you what we were able to do with the problem set and the tools available to us. So on this next slide here, I summarize it for us. So for this case study, this is the process we're going to follow. We'll start with SOLIDWORKS and perform a topology optimization on it to see what sort of geometry we can work with to meet our problem statement goals. The result of this topology study provides an interesting result that essentially shows that the component has a lot of extra material from which we can shell out. This shelled version will be sufficient in regards to our factor of safety, but we can add a lattice structure to it with the software called nTopology to make sure that there's minimal warping during the printing. The final model from nTopology will allow us to print directly in our HP printer, and the component can go directly onto the machine from there. So let's get to it. In SOLIDWORKS, we have the capability to run many different types of simulations, one of which, of course, is a topology study. A topology study is a unique type of simulation study that will remove material from your model until it has met the constraints of the simulation. For this study, we have used the constraints of the problem statement as the constraints of the study. We applied a 20-pound force to the front face of the component to simulate the force of the ball acting on the part. And you can see that in the picture here on the left. We've indicated a stripe down the middle of the component and applied a force to it to mimic the compression that the ball experiences through the action. We've taken that and then we've averaged the force over the entire area. On the picture on the right, we've selected multiple faces of the component to be maintained as they act as the mounting locations. So the topology study is going to continue to remove as much material as it wants until it meets the constraints of the simulation. One of our problem statement goals was that we needed to maintain all of the fastener holes. So you can see in the picture here on the right, all of my socket head cap screw holes are maintained and some of my larger dowel holes. All I have to do is select them in SOLIDWORKS and they're maintained. Okay, the only thing left to do for the setup is to set the overall factor of safety to 1.5 as the goal for the simulation. This parameter allows for SOLIDWORKS to remove as much material as possible until the lowest factor of safety in the entire part is 1.5. So the result of the topology study is pretty interesting actually. The study has presented that essentially all of the geometry that was the meat of the component is okay to remove, and essentially all that is needed is the small 2mm wall thickness we prescribed to maintain the geometry. So this leads us to a dilemma in our design for additive process. We have met the needs of the problem statement, and now we know that this model is 100% printable. In fact, on the right-hand side here, that picture is actually the component straight from the study in the build manager for the HP. So we know for a fact, 100% that this component could be printed as is. But given the amount of material that can be taken away, is this still the right method of manufacturing to use to address the problem? If we were to change the material to metal instead of the PA12 that the HP uses, we most likely could create the necessary model from sheet metal and other subtractive processes. But one other consideration to consider is that the design iteration needs to happen fast. So because of the time limitation in the manufacturing process, we still should use 3D printing. So with that being said, I'm going to perform a small amount of additional modeling to the component in order to stiffen the end result. So if we were to use a sheet metal process or some sort of subtractive process, it may take a number of weeks to get that sent out and then come back. Or if we were to do it in-house, it could take up to a week or 2 weeks. So we're still going to use printing because it's going to be a faster method. So of course, we've decided that we're going to move forward with printing the component, but we want to add a little bit of stiffness to the component so that it can't warp during the printing process. After all, that 2mm wall thickness we prescribed is quite thin, even though it meets our design criteria for the minimum for the factor of safety. The best way to add this stiffness is through a lattice structure, and that's best handled in this software called nTopology. While SOLIDWORKS utilizes the parasolid kernel to generate geometry, nTopology is an implicit modeling software that is much better suited to handle extremely complicated and detailed lattice structures. In order to use our SOLIDWORKS model in nTopology, we first have to create a shelled body that is close to what the topology study yielded from the beginning. Once we do this, we can then export the CAD file and then import it into nTopology. So on the screen here, I've got a picture, and then I've got 2 arrows. The arrow near the bottom is pointing towards the shelled model. The arrow on the top left is pointing towards the component of that body in which was removed in the shelling process. For nTopology, I can use both to create the lattice and then merge them together. So within nTopology, we can take that mass that was originally shelled and convert it to a lattice body. This style of latticing is called Voronoi and does well to add stiffness to your printed parts without adding a lot of mass. The reason we can add this style of latticing into our 3D printed model is because HP Multijet Fusion does not require supports in this printing process. No supports in the printing process allows us to create complex concave structures within our models that can only be created by 3D printing. nTopology will also allow me to export this model as a 3MF file, which is a 3D printing file, and then I can take this straight to be printed if I choose to do so. So in the past with subtractive manufacturing, there's no possible way to get these extremely complex lattice structures. There's geometry that has to be attacked from every angle, and it's very complex. 3D printing allows us to create geometry like this and think outside of the box to how things could be. So with this case study, we were able to decrease the factor of safety to around 1.5, which was exactly what the problem statement was asking for. Before, the factor of safety was around 6, which is plenty strong, but given the application, it wasn't needed. We were also able to reduce the volume of the print by almost 90%, which yielded in a huge mass reduction and a huge volume reduction. Last but not least, this entire design for additive process took 3 days to complete, from the problem definition to prepping the model to be printed. The print time for this component is around 5 hours, so we're still well within a week to have this out the door. If you have any questions about design for additive manufacturing or 3D printing in general, please feel free to reach out to us and we'd be more than happy to sit down with you and help you solve your problem, or if you have any questions about this webinar.